So the concept of exponential function. If the function is fx is equal to a to the power x and a is greater than 0, all positive real numbers, this is called general exponential function. And you have studied this in class 9. Here the domain, the value of x is all real numbers. Now we are going to discuss 3 cases. One case when a is greater than 1. Since a is greater than 0, 3 cases are a is greater than 1, a is equal to 1 and a is between 0 to 1. When a is greater than 1, this is the graph. You'll find it's a strictly increasing function. Second case, when a is greater than 0 and less than 1. A is greater than 0 and less than 1. This is the graph. You'll find it a strictly decreasing function. But you know, when a is equal to 1, then fx is 1 to the power x, always equal to 1. It's a constant function. So a is equal to 1, it's a constant function. A is greater than 1, strictly increasing function. And a is greater than 0, less than 1, strictly decreasing function. Now in these 2 cases, that is a is greater than 1 and a is greater than 0 and less than 1, that is a should not be equal to 1, either strictly decreasing or strictly increasing. It is called strictly monotonic function. And strictly monotonic functions, they are one-to-one function. This is the conclusion. That is, when a is not equal to 1, the general exponential function, it is a strictly monotonic function. In this case, increasing function strictly, and here strictly decreasing function. Now, one more case, when a is equal to e. You know the value of e is 2.7188, approximate value. It's an irrational number. Fx is equal to e to the power x. It is called natural exponential function. Remember, when a is equal to e, natural exponential function. And since when a is greater than 1, a is greater than 1, a is equal to e here, it is a strictly increasing function, we have seen that. And domain and real number, they are all positive real numbers. So just now we have studied that a to the power x is 1 function when a is not equal to 1. That is strictly monotonic function. When a is greater than 1 and when a lies between 0 to 1. When 0 and 1 is not inclusive, it is 1 function. Then only inverse function can exist. So this is strictly increasing function. We have done this in a is greater than 0. A is greater than 0, less than 1, strictly decreasing function. And a should not be equal to 1. Then fx, a to the power x, is invertible. Condition for invertible function is it has to be strictly increasing or strictly decreasing. That is strictly monotonic function. And that condition is achieved when a is not equal to 1. We have seen that with the graph also. Now, the property of graph, if log x to the base a is y, a to the power y is x, you have studied in class 9. A is greater than 0, a should not be equal to 1. This inverse function is called logarithmic function. Remember that. Log x to the base a. Domain is 0 to infinite, and this is the range of exponential function. That is why inverse function, 1 function exists. So we have to keep this in mind. Logarithmic function is not defined for 0 or negative real numbers. That is, x has to be greater than 0. It cannot be a negative number. You have studied this in class 9 also. So for the logarithmic function, when the base is e, then fx is equal to log x is called a natural logarithmic function. This should not be, you should not forget this. And it can be denoted either by log x or ln x. In this case, base will take it as e. And since e is greater than 1, natural logarithmic function is strictly increasing. This is the domain and this is the range. This is the concept of exponential and logarithmic function. So these are the formulas that we are going to use. The differentiation of e to the power x is e to the power x. X belongs to real numbers. Differentiation of log x 1 by x, x should be greater than 0. Differentiation of a to the power x log a, the condition is a is greater than 0 and a should not be equal to 1. We have discussed why. And differentiation of log x to the base a is 1 by x log a. X is greater than 0, a is greater than 0 and a should not be equal to 1. This differentiate with respect to x log here what I do, I will first differentiate log f(ex) with respect to f(ex). Then ex, and then differentiation of e to the power x with respect to x. This becomes 1 by f(ex), log x is 1 by x. This will be f dash ex and this will be e to the power x. Now at x is equal to 0, (1 by f e to the power 0), f dash e to the power 0 and e to the power 0. This is 1 by f1, f dash 1 and this is of course 1. Now we will find f1. f1 is equal to 4. So 1 by 4. F dash 1 is equal to 2. It's 2. So 2 ones are and 2 twos are. Answer is 1 by 2. Final answer is 1 by f dash x is equal to, I am going to use the product rule plus differentiation of e to the power x is e to the power x. Now f dash 0 is e to the power 0 g dash 0 plus this is 1, g dash 0 is 1 plus g0 is 2 and e to the power 0 is 1. It is 1 plus 2. This is the answer. So here we are going to use the product rule. Yeah. Let y be equal to so here I am going to use the product rule, x into differentiation of tan inverse x plus tan inverse x into differentiation of x is 1 minus the chain rule. First I will differentiate with respect to 1 plus x square and then 1 plus x square with respect to x. Therefore dy by dx is equal to 1 plus x square This and this gets cancelled, and finally we have the answer. This is the answer. So let y be this, and this is the quotient rule. Further, if I simplify, chain rule here, this is 5 to the power x, differentiation of log x is 1 by x, plus log x, and differentiation of 5 to the power x is 5 to the power x log 5. And here 2x 5 to the power x whole by whole square. Now 5 to the power x is common everywhere, so I'll write here 5 to the power x. Into 1 by x plus log x log 5 till here, and minus 2x log x. Similarly, 5x is common. This one I will write down here, x square plus 1 whole square. Now this x 5 to the power x x square plus 1 plus x log 5 and minus 2x square log x. From here to here, and this x square plus 1 whole square. So it's equal to this. First I am going to multiply the numerator and denominator with x plus the conjugate of this, a plus b whole square, and this is a square minus b square formula. I get this. Log a by b is log a minus log b. Now I'll differentiate. I can still write this as 2 log now I'll differentiate. dy by dx is equal to differentiation of log x is 1 by x and then I'll differentiate and this is of course 0. So I get here 2 by 1 plus differentiation of this can be further written as here this is cancelled. 2 by root of x square minus a square. Here I am going to avoid quotient rule. I think solution will become easier since implicit function differentiation you have studied. First I will do cross multiplication. Now implicit function differentiation you have studied. So right here, differentiation of y with respect to x plus y, and I'm going to differentiate here 1 by x plus, and then I'm going to differentiate here. I get differentiation of this will be x by root of x square plus 1 by x plus root of, here I get 1 plus x by root of x square plus 1, differentiation of root of x square plus 1. Now LCM if I take, I get this becomes x square plus 1 dy by dx plus xy whole by here 1 by here LCM this and this gets cancelled, this and this gets cancelled. What is left? By dx plus xy is equal to 1. This is, I can write here y is equal to e to the power 2 log x e to the power 3x, indices concept. This can be written as e to the power log x square e to the power 3x, and then y is equal to x square into e to the power 3x. Now reason is e to the power log x square is equal to x square. You have studied this. Now you are going to use the product rule. dy by dx is equal to common is e to the power 3x, 3x square is 2x. Further, if you want to take common, you can take x e to the power 3x. This is the answer. That is proved. This is the proof. Tan inverse 1 minus this portion is important. 4 to the power x is 2 square to the power x, which is 2 to the power 2x. This can be written as Therefore, y is equal to tan inverse now let 2 to the power x be tan t. So y becomes tan inverse 2 tan t by 1 minus tan square t, and this is equal to tan inverse tan 2t. This is the formula. Tan 2 is equal to t is equal to this. So y is equal to, and this will be equal to what? 2t. And what will be t here? T will be tan inverse 2 to the power x. From here, t will be equal to tan inverse 2 to the power x. Now, dy by dx, I differentiate 2 to the power x with respect to 2 to the power x, and then x. One by 1 plus 2 to the power x whole square, and this is log 2. This can be written as 2 to the power x plus 1, this into this, log 2 by, and again 1 plus 4 to the power x. This is the answer. So let y be equal to so I'll use the base changing formula, log by log x. Then quotient rule, dy by dx is equal to by log x whole square. Here log x and differentiation of this will be 2 by 2x minus 3 minus 1 by x log x whole square. Simplification, this x comes here, log x minus this will go there, by this is the answer.